In this video, I'm going to introduce instantaneous velocity and give a quick example at the end. So if we have 2 points, P1 and P2, we know how to find the average velocity between these points. You just take the points at P2 and subtract the points at P1. But what if I wanted to find a point like P3? How would we do this? Well, if we know P2, what we can do, our average velocity would look something like this. If I draw another red line, we connect the two, and we'd have our change in our variables form sort of a triangle like this. So this would be delta t, and this would be delta x. And what we want to do is find the velocity at this point only, not anywhere in between, but at this point specifically, hence the term instantaneous. In terms of graphing, we're essentially looking for the slope of the line at that point, where it only touches the curve at that point. And we call these tangent lines. But how do we do that? How do we get to this line? Well, we use something in calculus called a limit. And it has this notation. So we're going to take the limit of delta x over delta t. But a limit has to approach something. So we take the limit as a variable approaches some number. And what we're going to do is we're going to take the limit as delta t goes to 0. And I'll explain what this means and why we're doing this. So right now, delta t encompasses this range between these 2 points. And therefore, we have this slope. But if we bring delta t and make this 0, meaning that this point and this point are the same, what we're doing is dragging this point, P2, along this line and bringing it to P3. So we're basically saying as we drag P2 along the line towards P3, what is our function? As you see, if you imagine you're dragging this down, this red line is going to start to approach this line. So it's going to start to flatten out and become this line. And so in the language of calculus, the slope of something or the rate of change of something is called the derivative. Now the derivative, like I said, is just the rate of change of a variable with another variable. In this case, this is the derivative of x with respect to time, or t. So the change in position with respect to time, or the slope of the graph. And by definition, the rate of change of position with respect to time, the derivative, is velocity. And that is the definition. So let's do an example. And to do this, we'll have to know how to calculate derivatives. And I will show you, if you haven't done calculus, how we can calculate this derivative. So what we're asked to do is, we're given an equation of how our position changes with time. And we have this constant up front of 1 meters per second squared, just to make the units work out properly. And we're asked to find the velocity at 2 points in time, 2 seconds and 12 seconds. So first, let's graph this so we know what we're looking at. So let's say this is 1, 2, 3, 4, 5. This is time. And this is distance. Then we'll have 1, 2, 3, 4, 5, 6, 7, 8. We'll squeeze 9 up there. It's a bit messy, but we got 9 up here. And if you plug in t equals 1, you get 1. If you plug 2 in here, that's t squared, you get 4. Plug 3, you get 9, and so on. So you get a curve like this. And so we're asked to find the slope at t equals 2, which would be this red line here, which has a tangent at this point here. So how do we do this? We need to calculate the derivative of this function. So x equals t squared, and I'm not counting the constant for now. We'll add the constant in after. So to solve a derivative like this, we can use what's called the power rule. So we're taking the derivative with respect to time, which means we can bring down the power of 2, and then we subtract that from the power. So it'd be bring the 2 out front, and then in the exponent, it would be 2 minus 1 equals 1. And so if we write it out with our constant, which we should, dx dt is 2 times 1 meters per second squared times t. And now all we do is plug in our numbers. And I should add this is an equation now, which allows us to plug in any value of t, and it will give us any value for the velocity along this curve. So if I plugged in t equals 3, it'll give me the velocity at this point. If I plugged in t equals 2.5, it would give me the velocity at this point. So it's really powerful because we can find the velocity now with this relation for any moment in time. Like any moment in time, there's no limit. You could put t equals 200 million and you'd be able to know what velocity that this particle or whatever is going at 200 million seconds. So our velocity at 2 seconds is 2 times our constant of 1 meters per second squared times 2 seconds. So obviously that's going to be 4. And then the seconds, one of the seconds in the denominator cancel, and then the one in the numerator cancel, giving us units of meters per second, which is what we'd expect with a velocity. And that is our answer at 2 seconds. So this particle is going 4 meters per second at a time of 2 seconds. Now notice this is also, we don't have a direction, so this is the speed, not the velocity. Just a side note. Now let's calculate for t equals 12 seconds. So we get 2 times 1 meters per second squared times 12 seconds. And so now at 12 seconds, our particle is going 24 meters per second. And so that is how you do an instantaneous velocity calculation. It is essential that you know how to calculate derivatives, which if you haven't taken calculus, I'm going to try to explain the derivatives as I go through and do examples. But it's definitely worth it to know derivatives and limits when you do physics. So in the next video, I'm going to do another example, and maybe I'll do more examples in the following videos after that. But that's an introduction to instantaneous velocity. Thank you for watching.